Alright, welcome back to another AQA A-level chemistry video. Today I'm going to be doing a video on period-free oxides part 2, or more focus on period-free oxides. And yes, I know it's been a long time since I've done my last video, but a lot of things have happened since that last video. I've taken a bit of a break since I've been accepted to uni. If you've seen the community tab, I've been focusing on that. And now everything is all settled now. I know there's still a couple of videos left. There's like 8 or so videos left. I'm going to try and finish off all those videos. I'm going to try and finish off all the videos in this last section here. I'm probably not going to finish off the exam questions, but I'm sure you probably found other videos for that. And yeah, so that's how I'm gonna go straight into this video now. Try not to waste any more time. In this video, I'm gonna be focusing on the oxide melting point and the acidity of certain period-free oxides. I'm going to start off with the melting point. So the oxides of period 3 display a complex trend in their melting point. It's kind of similar to the period 3 elements melting point, actually, but some of them obviously have different reasons. But the first 3 metals, so the first 3 oxides are ionic and have high melting points. So you can focus here on the first 3. So these first 3 here all have ionic bonding, and it's due to the difference in electronegativity between the anions and cations. The greater the difference in electronegativity, the stronger the ionic bondage that you're going to have there, and generally they have the highest melting points. So magnesium oxide has the highest melting point of the 3, because it has obviously the greatest. You got here an Mg2 plus. First of all, if you check the Pauling scale, there's a greater difference in electronegativity between magnesium ion or Mg2 plus ion and an O2 minus ion. But it's also because of the fact that you've got here with Mg, it's an Mg2 plus ion, which has a higher nuclear charge and therefore a higher electrostatic attraction towards an O2 minus ion, compared to Na plus, which has a lower nuclear charge and therefore it have a lower electrostatic attraction towards a O2 minus ion in comparison to an MgO, in comparison to an Mg2 plus ion. So that's why MgO has a higher melting point, because it has stronger ionic bonding. Now you'd think with Al2O3 or aluminium oxide, it would have a higher melting point than magnesium oxide, since it's technically Al3 plus, which has a higher nuclear charge. Now the thing is with aluminium is that the electronegativity difference, so the actual Pauling scale, if you look at the Pauling scale, the electronegativity difference between aluminium and oxygen is smaller compared to magnesium and oxygen. So the aluminium ions attract the oxygen's electrons more, and this makes the bond partially covalent, and that lowers the melting point. So hopefully that makes sense. That you don't now. I don't see many examples where they want you to say that last part in detail, but it's just about understanding that aluminium oxide has a lower melting point than magnesium oxide, and it's because of the fact that the difference between aluminium and oxygen is smaller in electronegativity. So the aluminium ions attract the oxygen atoms, the aluminium ions attract the oxygen's electrons more. But it's about, if you don't remember this part, if you don't remember this part here, that's not the end of the world. But it's about understanding that it makes the bonds partially covalent. Because of that fact, because the difference in electronegativity, because the difference in electronegativity is small between aluminium and oxygen, it causes, I don't know why it's caused that. I don't know why it's gone up here. It causes the bonds become partially covalent, and that lowers the melting point. So that's the first 3 oxides. Now the second 3, silicon, phosphorus, and sulfur. So silicon dioxide is a giant covalent structure similar to silicon, or not a similar shape, but I mean it's similar principle as remember when we were talking about sodium, magnesium, and aluminium as elements, ionic bonding, it was general theme, and in silicon, it was a giant covalent structure. Is also here where silicon dioxide is a giant covalent structure and has the highest melting point of the non-metals in the third period. Now, why I say this difference is where obviously silicon dioxide has similar type of bonding. Silicon dioxide has similar type of bonding to silicon, obviously, because they're both giant covalent structures, but the strength is much weaker. Because remember, when we were talking about silicon as itself, silicon by itself had the highest melting point of the all of period 3, but silicon dioxide still has a giant covalent structure, but it's overall a bit weaker than compared to magnesium oxide and aluminium oxide. So just by knowing here that silicon dioxide is a giant covalent structure and has the highest melting point of the non-metals in the third period. So of the non-metals, it has the highest melting point, but definitely not the highest of all the period 3 oxides. So sulfur and phosphorus oxides have molecular covalent structure similar to the elements by themselves. So sulfur and phosphorus oxides have also a covalent structure, where P4, but the difference is that similar to phosphorus and I won't use that example. I'm just gonna talk about sulfur and phosphorus, oxides separately here, because I'm not gonna compare them to the elements. I don't want to confuse people too much, but I'll just say that silicon dioxide, giant covalent structure, highest melting point of the non-metals in this third period, whereas sulfur and phosphorus have a I say we don't really we usually, the word that I actually like to use instead of just saying it's a molecular covalent structure, I like to use the word simple. You can just get away with saying molecular covalent, but they won't take anything away from you from saying the words here simple. It's not a giant covalent structure. Simple molecular covalent structure. P410 has the highest melting point of the two because it has more atoms, so it would have a higher MR, and because of that, it has that more atoms there, high MR. It actually forms more and stronger van der Waals intermolecular forces. So this is one thing that I got from my teacher, because I was always confused. In textbook, they just say it's more no, that's not what I wanted to do there. In textbooks, they just say it's just more van der Waals intermolecular forces, but I just thought, sorry, it was just say, sorry, I'm gonna go back here. In textbooks, they would just say that there's stronger van der Waals intermolecular forces, but I thought that they were stronger because there was more van der Waals intermolecular forces. It turns out no, there's with P410, you're forming more and stronger van der Waals intermolecular forces in comparison to SO3 or SO2, which would have less and weaker van der Waals intermolecular forces. But if in the exam, I don't think they make a massive emphasis on you explaining the two. As long as you emphasize the point, there's either you say there's stronger van der Waals intermolecular forces or more van der Waals intermolecular forces. That's the big thing, because you'll definitely you'll very likely get a question in regards to why does the way they'll structure the type of question is by saying P410 and SO3 are both simple molecular covalent structures or molecular covalent structures. So why is there a difference in melting point between P410, which is here? You can see, as I said, let's look here, right? In green, SiO2, right, is a non-metal oxide here. Silicon dioxide is a non-metal covalent non-metal oxide. So is P410 and so is SO3. But why is, and SO2 here, I'm going to go to SO2 later. But why is it, I'm going to use a different color. But why is it there's a difference in melting points? Now, we know that silicon dioxide has a giant covalent structure. So that takes out of the equation. It has the highest melting point of all of the non-metal oxides. But that's explained because it has a giant covalent structure. But P410 and SO3 both have both of simple molecular covalent structures, or they're just simple molecular solids. So why is that P410 and SO3 have different melting points? And it's because of the fact that P410 has more molecules, or it has a higher MR, and therefore because it has a higher MR, it has more molecules. So it has more atoms. Sorry, I want to rephrase that. P410 has more atoms than SO3 or SO2, and therefore will have a higher MR, and therefore that leads to more van der Waals, more and stronger van der Waals intermolecular forces in comparison to SO3, and therefore we would have a higher melting point. P410 would have a higher melting point than SO3. So sulfur trioxide is a solid at room temperature, but but it also has a very very low melting point. So, and it's lower than phosphorus for the reason I just explained. So sulfur trioxide is the next one, and it is a solid at room temperature, but it has a very low melting point. So at room temperature you can find it as a solid, but it's very easy for it to start melting because it has a low melting point, and that's for the reasons that I just said. Now, SO2 is a gas at room temperature by contrast. So SO2 is a much weaker, much weaker molecular compound, because it's actually very it's not a molecular solid. Actually, I don't even count it as one of the molecular solids, because it's not a solid at room temperature. The difference between, look, SO3 is 16.9 degrees Celsius. Its melting point is 16.9 degrees Celsius, whereas the melting point of SO2 is minus 72 degrees Celsius. So there's a massive difference there. Now I'm going to go into the oxide, acid, and base behavior. So if everything I've explained up to here didn't make sense, or you didn't understand something I said, leave a comment in the video, because then it makes it easier for me, because sometimes I feel like I'm waffling or going too far ahead. I haven't done one of these videos in quite a while, so I have to get back in the groove of it. But if this didn't make any sense to you, or if I just over explained it, leave a comment. I'll try to I could always redo one of these videos. But I'm going to move on now to the oxide, acid, and base behavior. So the oxides of period 3 elements display a gradual increase in acidity along the period when dissolved in water. So the oxides of period 3 elements display gradual. Okay, so as you go across period 3, there's a gradual increase in acidity. They become more acidic as you move across period 3, when they dissolve in water. So some of these equations you need to be able to do in the exam. You need to know them off by heart, or need to be able to do them. Now the easiest ones are the sodium magnesium one. So sodium oxide plus water forms sodium hydroxide. That's the most basic one. By the way, if you're balancing you obviously have to be always balance your equations for A level. That should be a given. I shouldn't have to tell you that. But one thing I will say is that they don't really care about how you balance them. So as long as they're the same multiples. So in this case, it's one mole of NaCl plus 1 mole of H2O. Obviously, you don't write the 1, but you know what I mean. 1 mole of sodium oxide plus 1 mole of water goes from 2 moles of sodium hydroxide. If you had done 2 moles of sodium oxide plus 2 moles of water goes from 4 moles of sodium hydroxide, it would be a bit weird why you done that when you can just simplify it down to 112. But you would get the mark. They wouldn't take a mark away from you, as long as you don't start being weird about it and start doing over the top calculations. But if you're worried about rounding it down, they do accept multiples. So the person marking you would accept the multiples. So sodium hydroxide is a strong base, so the pH of this solution will be between 12 to 14. So the reason why, so when these obviously when you're reacting an oxide with water, you form either an acid or a base, or you don't get anything at all if it doesn't react with water, because if it reacts with water, you'll form one of these acids or bases. If it doesn't react with water, as we'll see later on, then you won't get a so if it doesn't react with water, you won't get anything that will you won't have any product. You won't have a product that will act as an acid or a base. It'll be just probably be a salt or something like that, but more likely it won't react at all in solution. So sodium hydroxide, I've already said this one. Sodium hydroxide plus water goes from sodium hydroxide, but as you can see here, the sodium oxide in water, we say that sodium oxide is basic because when it reacts in water, it forms sodium hydroxide, and we know that sodium hydroxide is a very strong base. So the pH of this solution would be between 12 and 14. If you want to test for the presence of sodium oxide, you can add sodium oxide to a solution of phenolphthalein, and it should change color from colorless to violet, proving that there's a basic reaction occurring where we're increasing the amount of base in our solution. If you wanted to do that, because we know sodium hydroxide is a strong base. Now, magnesium hydroxide with magnesium oxide, so magnesium oxide plus water goes and forms magnesium dioxide or magnesium, magnesium, sorry. That's the magnesium dioxide. That's not right. That's not right at all. Magnesium oxide plus water goes and forms magnesium hydroxide. So magnesium oxide is also basic because it forms magnesium hydroxide, but magnesium hydroxide is a weaker base. I'm not gonna go explain why magnesium hydroxide is a weaker base. I've done that probably in another video, but magnesium hydroxide has a stronger attraction to the Mg2 plus has a stronger attraction to the OH minus ions, so it doesn't dissociate OH minus ions as strongly in solution. So magnesium hydroxide is a weaker base. But anyway, the point being here is that you can see you're forming magnesium hydroxide, which is a weaker base. So magnesium oxide is a basic compound, but not as basic as sodium oxide in solution because it doesn't form and it doesn't form a strong it doesn't form a base that's as strong as sodium hydroxide. So magnesium hydroxide is a weak base, so the pH of the solution will be anywhere between 9 and 10. Now, aluminium and silicon, the oxide of these elements don't react with water, so we don't really count them. We don't really look at them as much when we're talking about how they react with water. However, with now we're becoming more acidic. We're going from basic to acidic. So P410 forms of P410 plus 6H2O goes and forms. Now remember to always balance your equation. So P410 plus 6H2O goes to form 4H3PO4, and this is phosphoric acid, which is a very very acidic. It's triprotic even. So it's triprotic acid that we're forming here. So phosphoric acid is formed in this case. Some of these you can already see already. You can see directly. SO2 plus H2O goes to form H2SO3, and this is called sulfurous acid, which has a pH between 0 and 2. And SO3 plus water goes and forms H2SO4, and this is sulfuric acid, which is one of the most strongest acids. I wouldn't say as strong as H3PO4 though. H3PO4 is a strong acid that's triprotic, so I assume that's more acidic. But the point being here, I'm probably extending this more than it has to be, but I think you can already see the trend that's going on here between SO3, H2O, and between the oxides of these non-metal oxides and water, and how they react with water, forming more acidic compounds in solution. Here we're forming sulfurous acid, phosphoric acid, and sulfuric acid, very very strong acids in solution that have pH between 0 and 2. So sulfur oxo acid structures. So these are just structures of sulfuric acid on the left and sulfurous acid on your right. So above the structures of sulfur oxo acids, both are diprotic and will lose 2 protons in solution. And obviously I have phosphoric acid, triprotic, so lose 3 protons in solution and form a trianion. Hopefully this video was helpful. I know it's probably not my best video that I've just done right now. I'm coming back, so bear with me a bit, but yeah, bear with me a bit. I will try to make better videos though. This is definitely not one of my best videos.